amorphous Psi-CN nanocoatings by A.S. Bhattacharya, CUJ, India. Lecture, Scratch Adhesion Behavior of Amorphous Psi-CN Nanocoatings. Welcome everyone. Today we'll be exploring the scratch adhesion behavior of amorphous Psi-CN nanocoatings, a topic of growing interest due to the material's application in MEMS, microelectromechanical systems. The discussion draws from both experimental observations and simulation insights, including finite element modeling, VM, and molecular dynamics, MD. Slide 1-2, title and abstract. Psi-CN nanocoatings exhibit high hardness, thermal, and chemical stability. Our focus is on adhesion behavior during scratch testing on two substrates. Silicon 100, stainless steel. We'll assess this using progressive loading scratch tests, finite element modeling, molecular dynamics, MD. Introduction. Key motivations. Scratch adhesion testing is a crucial mechanical reliability check for coatings in microdevices. Adhesion is influenced by coating thickness, substrate properties, residual stress in the film. Slide 4. Experimental methods. Deposition techniques, plasma-enhanced chemical vapor deposition, radio frequency, RF, magnetron sputtering. Scratch test parameters. Progressive load from 1N to 30N null. Monitored acoustic emission and coefficient of friction, COF. Slide 5. Characterization techniques. To assess coating failure, SEM and optical microscopy used to inspect morphology of scratch tracks, acoustic signal analysis, and frictional force measurements pinpoint failure events. Slide 6. Scratch track analysis. 3 regimes during scratching. 1. Elastic deformation. 2. Microcracking. 3. Delamination. Critical loads, LC1, first visible cracking, LC2, full delamination. Observation, LC values were higher for SI substrate, indicating stronger adhesion. Slide 8, Figure 1, SEM scratch track. The SEM image shows initial elastic deformation zone, progression to microcracks, finally delamination of the coating. This visual aids in correlating mechanical load with physical failure. Slide 9, Figure 2, FEM stress contour. The finite element model FEM reveals high stress concentrations near the coating substrate interface. These stress zones act as nucleation sites for interfacial delamination. Slide 10, Figure 3, COF versus load graph indicates COF increases with load. Critical loads, LC1, LC2, are marked by sharp spikes. Chip ejection also observed around these critical points. Slide 11, Figure 4, crack evolution, schematic breakdown of failure stages. Radial and lateral cracks grow stepwise. Lateral cracks dominate due to radial shear stress. Understanding crack evolution helps us design more durable coatings. Slide 12, simulation insights. FEM simulations. Validate the experimental stress patterns, help visualize failure progression. Molecular dynamics, MD simulations. Show atomic level crack propagation, highlight the role of radial shear in delamination. Slide 13, conclusions. Adhesion strength depends strongly on residual stress in the film, substrate mismatch. Optimizing film substrate pairings and deposition processes can enhance MEMS reliability. Slide 14, references. 1. Bhattacharya A.S., Surf Topographer Metrol Prop, 2020.